So let's start as usual. We try to solve problems without local testing. If we solve all the problems of the contest without local testing from the first try, it's a win. So this looks scary actually, but we'll try to solve all the problems. Let's go. Melted mix graphs of gold beacons and signal to produce new metal. What metal did he produce? Pure gold, pure silver, or an alloy? Silver or alloy? So if B is 0, I should output gold. If A is 0, I should output silver. Else I should output alloy. Okay, good start. What's next? Again, 4-digit pin, okay, which maybe begin with 0. Okay. Pin is said to be weak when it's quite well. Oh, I hate problems like this. So it's one of the following conditions. At least one, I think. Okay. All of the 4 digits are the same. For each I, such that from 1 to 3, next digit follows X. What is follows? So it's next digit. Okay. Follows. For each and 0 follows 9. So if I have 2 consecutive digits, which next one is follows the previous one, it's also bad. Don't get it. For each. So if I have all 4 consecutive digits, okay. So this is strong, but this is weak, okay. Okay. Okay, let's do it. No, it is like false, yeah. So if I have 2 different digits, so if Si equal to S0, then I want to put 2 true. Просто в Яндексе неплохо. Надеюсь, что помогло. Не знаю. Не знаю, что там спрашивают в Яндексе на стажировку. Если поступил, значит помогло. Okay, now if strong. Now I need to check if I have 4 consecutive digits. No. Let's do it separately. So no. So here we check the first condition, here the second condition. Yeah. Again, so false. Now do this. No, I'm so sorry. No, it's not. That's weak, equal false. So if it is weak, then I'll put weak. Yeah, like this. And now again. So now I need to check if these two digits are consecutive. So we need to check if y equals to x plus 1 modulo 10. If it not equals, then it's not weak. What am I doing? Like this. Yeah. And then again, if it is weak, then it's weak. Yeah. Yeah. Okay, what's next? Given two sequences A as n positive digits and B as m positive digits, find the minimum difference of element A and element of B. That is minimum of this. That's interesting. No, it's classical problem, but we can use two pointers method or binary search. What do you prefer? Let's use two pointers method just for simplicity. Or maybe not. Just thinking. Let's use the binary search just for simplicity. So we iterate all elements in array A. Now we need to find the optimal value in array B. So we'll make a binary search like this. So that's the first element of array B greater or equal than x. So we will say if I is less than m, we will update the result like this. Minus difference, no, like bi minus x. So we find the first element greater or equal than x, so we know this difference is optimal, and we need to now different from other side. So if a is greater than 0, then we have the previous value. So we will update result in its. Like this. Yeah, so it's differences. Yeah, that's fine. Yeah. Cool. So another solution is to use two pointers method. So you can do it like this. And the I is less than x, you move the second pointer. So this is the first pointer, this is the second pointer. And again you check. Let's do it again here. Just do it. I'll just do it all the time, just to be sure. It totally should work. Maybe this is too much, but no. What was the problem here? If I have elements, so I find the closest element which is greater or equal to x. Minus b, okay. Yeah. Makes sense. Yeah. Just another way to solve this. So now this part is linear. It was n log n, but now it's linear. But we still have n log n here, so it's not a big deal. The solution have the same time complexity. I think it's it's slightly faster, but not a big difference. Okay, what's next? Balls on left and written on back. Initially, the back is empty. But if I equal to m is possible, if I equal m, I immediately break. Just to make sure. So if my second pointer comes to the end of the second array, it means I found all the optimal solutions, so all other elements of array A will not be optimal. How to solve it in linear time? I believe it can be solved in linear time. Yeah, I think I can prove it. So you can prove that it's not solvable faster than sorting. So to find the closest parent to arrays, you need to sort this arrays at least. Can I prove it? I'm not sure actually. Maybe not. It looks like it's impossible to solve it faster than an log n time. I'm not sure how to prove it yet. I think you cannot solve it faster than log n time. After I++, here I might have yep. So here I haven't defined behavior. Yep. Yes, you're right. That's why I never write it like this. Actually, you should never write it like this. So it's not a safe way to do it. So usually you do it like this. You find this optimal value of I and then make this check and then make this check. Something like that. But you also need to check the previous elements. So after it is 0, so you check the previous element. Something like that is more safe way to do it, I think. So that's the most safe way to solve this problem. Yes, that's why I solved it using binary search, because it's much more safe way to solve the problem. If you can avoid using 2 points method and use binary search instead, that's fine. But sometimes you kind of have to use 2 points method because you have time limit is very strong, or if you have some others, maybe you can just use 2 pointers. So sometimes you just must use 2 pointers method to solve the problem. But if you can avoid it, it's fine to avoid this problem. Okay, let's move next. Yeah, you can make bug in binary search as well. Binary search is not an easy algorithm as well. So even with binary search, you need to be careful to do it, right? Because you have these corner cases. So if your binary search is out of the border to the right or out of the border to the left, it's actually not that easy. So we still have this. So this part is the same as we had in the binary search solution. So only this part changes. Again, it's cool. It's cool when you have different approach to solve the problem. You can choose approach for your concrete problem. When you have many ways to solve the problem, you're kind of more mobile in your contests. So there's much more probability that you will solve the problem. Yes, in Java you have no. It's not wrong, but it's not usable. In Java binary search finds exactly your value. It's just some. No, it returns something strange. I don't remember. Yes, but yes. Java binary search returns something very strange. Lower bound in C++ is much more easier to understand what's going on. Because maybe both switch, nothing is written, and one bag. Initially, the bag is empty. Takashi will do Q operations. Okay, it can follow 3 types. Yes, so insertionism but negate. Yeah. If the element is in your array, it returns you in positive value. If it is not, it returns you some negative value. Very strange logic. Average ball, replace integer written on it with integer plus xi. What is xi? So I have some values x. So I have some. So each query has. So okay. So xi is some value. I don't have to choose operations. I have these operations. Okay. Write integer. Put it in the bag. Okay. For each ball in the bag, replace with plus xi. Easy. Pick up the ball with the smallest integer in the bag. Record the integer written as well and throw it away. Easy. For each you are given the type P and expression. So print the integer conversion. Make it just correct, but they corrected algorithm in binary search in Java. I have no idea. What? Okay, no, it's not that important for today. I'll check it later. Yeah, that's interesting. Let's move with the problem. So in this problem, we need to maintain a set of integers, and we need to have three operations with the set. Add integers to the set, increase all values in the set by the same constant, and find the minimal element in the set. Minimal element in the set. Okay, I'll find the link. I'll check it later. Yeah. I'll solve this problem first. So in the beginning, I have an empty set. Okay, I have an empty set and I have few queries. So now I have the query. So I read the type of this query. So if this type equal to 1, I add something. If type is 2, I increase something. Else I return the minimal value. So how I'll solve the problem? Very easily. I will maintain the set and the shift. So I will maintain two constants. So I will put two things. First thing is multiset. T-set. It's 10 power of 9. So they may be very big. So if I do it 12 times, so I make multiset of longs. So it will be my set of my integers. And now I need to be able to increase all integers in the set by the same value. So instead of increasing all integers, I will maintain the shift. So I will maintain another long threshold shift. So not delta. So the real values in my multiset will be these values plus this delta. So now how to, for example, here, let's make this version. If I want to increase all elements in my set by these deltas, so by this x, I will just increase this delta. So increase delta plus equals. And that's all. So this delta will be the shift of all my elements. So my elements on the shift, the real values in my set will be values in S plus delta. So if I want to increase all elements in my set, I will just increase this delta. So all real values will be increased by delta. What's happening here? Now I need to add value x to my set. Instead of the real value must be x, so value in my set must be x minus delta, right? So if I add this value to set S, then the real value of this element will be this plus delta, so it will be x. And finally here, what's going on? So now first I'll find the minimal value. As begin plus delta. So this is the minimal value in my set. So this is the value in my S plus delta is the real value of this element. And now I need to remove this element. So I will erase S like this. So I remove the first element of my array. I believe that's all. Well, I'll check this story later. Write 3, write 5, check, so it's 3, increase by 2, so now it's 7, Looks fine. Yep. Cool. So what's next? What's happening here? We're solving the problems. We have problems from at-quarter beginner rounds. This is at-quarter beginner round. Which one? It's the last one. How to find the link? I don't know how. So it's 212. The Republic of Headquarters and cities called City 1, City 2, City N. Initially, there was a bidirectional road between every pair of different cities, but M of these roads had become unusable during the time. More specifically, so we have a full graph and then remove some M edges from this graph. And we'll go for KD trip, which starts and adds in City 1. KD trip starts in City 1 is sequence of KD cities, 0 equal to K. And for each one, this difference is still usable road connection situations. Makes sense? Print the number of different K trips starts in City 1 model. That's here K trips. This is basically different. Oh. So graph have this big graph, 5,000 by 50%. Some roads are removed. At most 5,000 roads was removed. So it's almost full graph. Yeah. And now so what's the usual plan? So if I have another constraint, so if I have just small number of roads, so if I have M roads instead of N, if here I removed M roads, so graph is almost full. But what is if graph was sparse? So if M is small, so if the number of roads in my graph is small, then how to solve this problem? Let me show you. So what's the usual way to solve this problem? So when you have graph and the number of edges is small, so what you do? Have just a small number of edges, like this. So what you do is to calculate number of ways for each k and each node. So you calculate something like this: d and v and k. It's the number of ways to get to. So you start from node. So you start from node 1, yeah. So you start from node 1 and make k transitions and end to vertex k. And here you have k moves, yeah. And this value will be the number of paths like this. And now how you recalculate this value? You're using dynamic programming. So if you're standing here, you look on the previous node, on this node u. So it will be sum for all these nodes u, so it will be d to u for k minus 1. Yeah. For all nodes connecting to this node v. So we iterate all edges connected to node v, and for all this, for each such edge, we take the previous node, get the number of paths like this, and take the sum of all aspirations. It's not focused. Again, I hate it. What's the problem with this focus? No idea. No, you don't need to have matrix. You can make yes. Sometimes for the problem, if this k is big, you need to make something like matrix exponential house code. But here k is small, but the matrix is big. You cannot multiply two matrices 5000 by 5000 in this time limit. So you need to find some other solution. So again, every time you see browse problem, it depends on the constraints of it. So if n is small and k is big, you need to make matrix multiplications. If this n is big and by k is small, you need to do something different. It always depends on these constraints. So what we'll do here? Here we'll see that k is small, so we can make k iterations. So for each new iteration, we will calculate the number of these rows. And usually you do it like this. So if m is small, so the time complexity of this method is 1. So on each step, we take each node, and for each node, so we have n steps, we have k steps. For each step, we make m iterations, yeah, because we take each node, for each node we iterate all incoming edges. So the total time complexity will be k multiplied by m. And it should be fine for this. So we have 5000 here and 5000 here. So it's fine. But here we have different problem. Here we have problem when we have m is not the number of edges, but it's number of missing edges. So we have the full graph, and then we remove some m edges from this graph. But if you know how to solve this problem, you kind of need what way to think about. So we will try to do the same thing, but using these constraints. So here, instead of iterating over all edges in the graph, we will try to iterate over all missing edges in the graph. That's what you can do. You can iterate over all missing edges in your graph. You know, you have the full graph, but then you remove some m edges from this graph, and you can iterate over these m edges. So you'll have 5000 edges here. Why did they give the complement graph? Because they can. No. Again, there's always the constraint is very important part of the problem statement. So you always not only look in the problem statement, but you always need to look in the constraint. Your solution depends on the constraints of your problem. In this problem, what's the main idea of this problem is that you have not a sparse graph, but you have almost full graph. So your graph is almost full. You have the full graph, and then you remove some small number of edges from this graph. So that's the idea. So you need to find fast algorithm for these types of graph. Yeah. No. It's not because they want to keep the input small. That's exactly because they want you to find a solution which works for these specific types of graphs. So they want you to find optimal solution for the graphs which are almost full. You can Google it. It's no problem. So that's all. So we need to think about solution which works for these types of graph. So for the graph which are almost full and have some small number of missing edges. So what we'll try to do? We'll try to do the same thing like here. But we will modify this algorithm to work for our case. So for our case, we'll calculate the same number. So we'll calculate the same number, but we will, again, in classical algorithm, you want to iterate over all edges incoming to your node V. So you have this node V, yeah, this node V. I want to take all edges to node V, and take the sum of this value. So I need to take sum for all nodes U which have incoming edge to node V. Now, I don't want to iterate over all edges. I have too many edges. So I want to iterate all missing edges instead. So what I can do? I take node V. I have these edges. And I have small number of missing edges. So I don't have edges to these nodes because these edges are missing. So instead I will iterate over these nodes and subtract this value from the total sum. So I want to find sum of these elements, yeah? But I don't want to iterate over all edges here. So instead I will take the whole sum of everything and subtract this number. So I will subtract this sum from the sum of all elements and this will give me the sum of this set. That's quite common trick. Again, the trick is the following. You want to calculate sum of some set. So you want to calculate this sum. This sum is formed like this. You take the big set and then remove some elements from this set. So instead of calculating the sum of your set, you calculate the total sum and then subtract these elements from this sum. And this will give you the sum of your set. That's what we will do. We will calculate this sum like this. We will take the sum of all elements and then subtract the missing elements. And this will give us this sum, and time complexity will be the same. How do you get that number which subtract? We'll just simply to iterate. We can iterate over these elements. Again, you can take these elements and iterate over all of them, because the number of missing elements is small. We take almost full graph. We have a lot of edges here and small number of missing edges here. So we'll simply iterate over this set, and the time complexity will be m, because the number of missing elements is m. That's all. That's the plan. I'll try to implement it. I need this paper. I want to keep this paper actually. I'll move it here so you can see what's going on. N, M, K. So we have N, M, and K. And now we have these pairs. I'll do it like usual. That's how I usually implement graphs. Int x and y, x and y, x and y. And now I do x push back y, and gy push back x. Are they all? Yes, they are all distinct. Yeah, all pairs are distinct. So I don't need to take care about this. Yeah, that's all. So that's the base of our dynamic programming. So for the first phase, we have one way to start in the node 0 and 0 ways to start in all other nodes. And now we just integrate all. So, okay, plus. GN, thank you. That would be a shame to have wrong answer for this bank. Model. We'll just for simplicity. So we iterate, or let's make it v like in our paper. So we take some node and we need to calculate this value. Yeah. So value v should be the sum of this. So we take the total sum. So this is the total sum of all elements, and now we just take the sum of all elements and then subtract all elements. And also subtract b. Yeah. So we subtract all missing edges and we subtract the value in our node. And this will give you the values of sum of values in all nodes which have edges to our node. writing modulo n. This. Yeah. What's wrong? Okay. That's all. Now we just need to find the answer. So we need to end in the local source. So the answer will be d0. So if just in case, because I subtract something, maybe I have negative value in the end. Just to be sure. Because here I have minus. It should be still fine, because yeah, the sum should be positive. Yeah, because I don't have modulo here, because I'm lazy. Usually you have a modulo here, but I know this value will fit in 64 bits, so it's fine. So this sum will fit in 64, and here, so it should be non-negative here, and it should be non-negative here. Yes, I have special local library for modular calculations, but I usually don't use any pre-written code in these streams, just for simplicity. Just to show you that you actually usually you don't need any pre-written code in these easy contests. Yeah, but if you have pre-written code for modular arithmetics, you should definitely use it here, just to be sure. You just use this modular arithmetics here. This model usually you have something like special class, like int, something like that, and you just override all the modular operations like plus, minus, multiplication, and so on. That's much more safe way to solve these problems if you are doing it in the real contest, but I'm not real in contest, I'm just practicing. I have speech fill. Since I moved from Java, I use this define just to be sure that I never use long. That's one of my problems. Wait, I submitted. I didn't check. Okay, usually I read the code before I submit it, but okay, that's fine. Do you still use Java? I don't use Java in real contests usually. I used last time we used Java. It was in hash code, because in hash code it's not about the not about the fastest code. It's more about the code is big, so it's much easier for me to handle big code without any small bugs if you do it in Java. But in this algorithmic contest, usually time limit is very small, so you kind of need to use some fast language. And when I used Java, it was always so when I used Java, it was always a problem that you need to write the optimal possible code when you write code in Java, because the time limit is set for C++ solutions. N cities and M buses. Okay. Bus departs from city at time SA plus to have city best time. Okay. Will travel between these N cities when he is in city P at time T. He will do the following. If there is a bus which departs from city P not earlier than time T, take the bus that depart the earliest among those buses to get to another city. If there is no such bus, do nothing and stay at city P. there are multiple buses, repeats doing the above until there's no bus to take. It is granted all buses depart different times. Okay, so the bus do take it always uniquely determined. Okay, a gate digital time needs to change the bus is neglected. Okay, here's your tag process Q queries. It just follows. If Takashi begins his travel in city at time X, in which city or on which bus will he be at time Z? Ah, purpose block and sequence. My bad. This looks like quite simple problem. You need to be careful because you have two cases. You may end up in city or you may end up in the bus. Ah, so that's why this is false. So you never you're never in the middle. So in each 0 time point, you are either in the city or in the bus. Okay, how to solve the problems like this? We'll use binary lifting. Quite simple. So each state is uniquely determined. So you start at some point. If you are in this bus, then you will go to this town and then move to this bus. So for each bus, you know what will be the next bus. So the next bus will be the earliest bus in the point of your destination. So that's what we'll do. We will calculate for each bus the next bus we will be if we use this bus. And then we'll build this tree of buses. And in this tree, we need to find the point we want to be in time Z. That's the plan. So first we will build a tree of buses. So for each bus we will find the next bus. This graph will be a tree, obviously. Yeah? So we'll build this tree of buses. And now in this tree, we need to find the position at specific height. So we'll start at this point, find the position at this height. We can do it using binary lifting in the trees. It's actually quite simple. So we have N, M, and Q. Now we have the buses. For iterator all for mi++. Yep, and we have A, B, S, and T. Yeah. Okay, now we need to travel from A to B, start at S and at T. I'll just multiply them just for simplicity. So the start time is actually S plus 0.5, so I will do S equal to S multiplied by 2 plus 1 and T equal to plus 1. Just for simplicity, so keep everything integer. So now all times are integer. So here I have half integer times, yeah. So I will multiply it all times by 2, and all times are integers now. So these times are integers, and also these times will be integers. These times will be integers. This one. Which one is time? So Z is time. So this Z will be integer. let me think for a second. I will just put this everything in the array. I want to have a structure for this. Yes. Like this. So now I have an array of buses. Now we need to build this tree. So for each bus, we'll find the next bus in the tree. Well, let's go. How to do it? We will, for each node, we'll maintain the set of buses. Vector of pair and int. So this will be basically a graph of size n. So for each bus, so for each bus, we will put it into this list. So g of bus A will push back pair. I don't know this. I want to have the index of this bus. So I take the start of this bus and push the pair with starting time and the index of the bus. Now for each node, I know the list of all buses starting from this node. Now I iterate all these nodes and sort these lists. That's all. And now we need to find the next node and so we'll maintain the of parents. So P will be the parent of my node. So it will be M minus 1. Now for each bus, we need to find the parent of this bus. So how to find the parent? We need to find. So the next node will be BIB. So we need now in node X, we need to find the smallest value X like this. Lower bound begin JX. Can I do it like this? Yeah. And I want to find EIT. Yeah. I just want to have indices. Yeah. So this is the index of these elements. So if this j is less than x size, then I have this index. So this will be the next bus. So p of I should be the index of this element. So it will be xj second. What? Why is it even working? So X is an array of pairs. How can I find? How can it compile? So I need pair here, right? don't get it. So X is vector of pairs, right? And now I find in vector of pairs. So this is a pair. What's wrong with it? Pair of int and int. What's your problem? Sometimes C++ is strange. Is it fine now? Okay, it's fine now. So here we find the next bus for each bus. Now we build this string. Now what we need to do is to build a binary lifting. So how to make a binary lifting? That's usually how I implement binary lifting. I have the constant number of steps in binary lifting. So you need log n steps in binary lifting, but I usually don't calculate this log n. I just use constant number of binary liftings. So in my case, when I have 10.5, then the logarithm of this will be about 17, right? Yeah, it's about 17. So I will make like 20 layers of my binary liftings, and that's fine. And maybe I have bug. You can check this. It looks fine. So in this list X, I try to find the smallest element greater or equal than this pair. This pair is my time and 0. So it will be the first bus starting from not earlier than this time, right? Looks fine. Yeah, we'll check. So we're just going to this jump pointer. So we need to have this number of layers, and for each layer we will need to make jump from each point. So jumps from 0 points is just speed. No, I don't want to do this. I don't want to have this minus ones. I want to have jump. I want to have pointer to itself. If not, so let's make it pointer to itself like this. Why do I have reference before x? What does it mean? What does it mean? What does it mean? Well, it means I want to look in this vector. So this x is a reference to this vector. Okay? Isn't it how it works in C++? I'm not a big master of C++. I think that's how it works. So it means that here I always use this vector instead. Yeah. Why do you think it's wrong? So I need to take this vector and find this value in this vector. So I say that x is a reference to this vector. Yeah. No. If you know a better way to do it, you can say, but I'm not a master in C++. So jumps on the first layer will be just our parents, and on each next layer we will calculate jumps like this. We'll take all nodes, m. We have m nodes, and for each node the jump on layer I will be 2 jumps on layer I minus 1. So we make jump layer I minus 1 from J, and now we make another jump on layer I minus 1 from this person, like this. So we just double these jumps. That's all. That's all. I will answer the queries. Now we have these queries. So each query is x, y, and z. So what is what? So y is the city. So we'll make y minus minus. Yes. The whole point is that this doesn't create a new vector. Yeah. So we don't. If it creates a new vector, then we will need to spend too much time to create a new vector. So it's most like a pointer, but not exactly. So x is time, so x should be equal to x over 2, and z is also time. All times up to 10.9, so it should fit. Okay. Now we need to find the first bus, which we will do. So we will take this. Take this bus. So we take the list of buses in city Y. In a letter, let's use some letter H. No particular reason. So we'll find the first bus which we use if we start in city Y at time X. Now we take this bus. If there is no bus, if there is no bus, then we just stay in this city. So we output. We need to output. What we need to output? A bus attempting to integer space in city from which bus in city just number of city. So number of city will be y plus 1 because we number cities from 0 and they from 1. Continue. Now if we have some bus, then we have this bus. Yeah. So we take this bus and we say don't like this. So we take a bus with index h, j, second. I will use all letters today. So this is the index of the first part. So if we departed later than z, then we just stay in this city again. Okay, now finally we take this bus. So we start in city Y. We start in city Y, wait until this bus came, and then take this. You forgot to read queries. Thank you so much. That's the most common problem in these streams. So we wait until this bus came and then use this bus. Now we need to find the last bus in a row. So what I will do, I will try to find the last bus which I will use. So I start in bus K. So K is the first bus I use. Now I'll find the last bus I use. So how to find the last bus I use? I will iterate all binary liftings. So from max minus 1. And now for each binary lifting, I will try to make this jump. So I will take this new jump, so it's jump from K. Now I will see if I use this bus or not. So if I use this bus, if its starting time is less than Z, then I will use this bus. Then I'll make jump to this bus. So K equal to K. That's all. That's binary liftings. Now I find the last bus I use. So K is the last bus I use. Now I will check if I'm at point Z, I still in this bus. So if this bus, if Z is less than this, yeah, it means I end up in this bus. So I will answer this bus as an answer. So the bus A plus 1. It's not Java, BKB plus 1. Else, I will end up in the final system. So if not, it means I finish in this city and then wait for the next bus. And the next bus will not come. Looks fine. Oh, it was problem F. We have 2 more problems, and the last problem is okay. So we have 2 more problems. This may take longer than expected. I need to stop the stream at 8, so we have like 45 minutes left. Okay. Will you have game theory lectures? That's interesting. I will have at least 1 lecture during this 3rd semester. Maybe we need to have a special lecture about in Codeforces. I'm not actually a big specialist in game theory, so I know something about game theory, like normal things like this retroanalysis or Grandi functions, stuff like that. But I'm not that good expert in game theory, so I would rather find better person for this. But when will next person? In September, 1st September we'll start the new semester. I will make a special post about it. Given a prime number p, I hate the problem sites like this. How many pairs of integers satisfy the following conditions? Okay, so I have 2 integers modulo p. There exists a positive integer n such that x. I hate problems like this. I have no idea how to solve problems like this. How many pairs? So for each, so basically for each x, I want to calculate the number of distinct powers of this x. Yeah. No idea. What I can do, I can factorize p minus 1. This looks like a good start. So I can take p minus 1 and I can factorize it. Oh yeah, I'll just think with you. So what's going on? So you have this number x. So if you look on this power, x x power 1, x power 2, and so on. Then at some point you have x power p minus 1, which equals to 1, and this equals to 1. So this length of this period is at most p minus 1, but it can be shorter because you can, this length of this period is p minus 1, but the length may be some divisor of this p minus 1. So for some x's, you may have some 1 here. So you have this 1 here, and you may also have 1s here. So this length is p minus 1, but the length of the period may be some divisor of this p minus 1. So what's happening here, for each x, the number of this y will be some divisor of p minus 1. It may be p minus 1 or some divisor of this p minus 1. That's what's going on. So we need to take sum for each x, either pi minus 1 or some divisor of p minus 1. But which divisor? That's interesting. So what we can do, we can iterate over all possible divisors of p minus 1. So we can iterate over all these things. So we can look at this thing. Now let's call it something like d. So let's call it d. We can iterate over all possible d's. There are like square root of and so on. Yeah. So not many of these values d. Now for each value d, we need to find x which have period d. So we need to find such x that x is in power of d equals to 1. Modulo p. How to do it? I have no idea. I actually have no idea. So if you look here, for example, for this 3, again for it, no, 0 is separate case. For 0 it's always 0 0. For 1, the length of this period is 1, obviously, and for 2, the length of this period is 2. So p minus 1 is 2. So for this 1, the length of the period is 1. For this 2 is 2. And we have 40 minutes to solve this problem and the next problem. If g is some primitive root, then yes, if g is some primitive root, okay, then oh, that's a good point. So if we found some primitive root of this, so g is a primitive root. Primitive root means that the length of this period is p minus 1, basically. So we can take some value which have period p minus 1. And so if you look on the powers g 0, 0, 1, and so on, gp minus 2, you will have all possible p minus 1 values, except 0, obviously. So if in this list you have some x, then so x is g power k. P minus divided by k. Not exactly. That's not exactly true. It's not divided by k. It's divided in this modular thing. So x in power d should be g in power kd. Yeah? It means that and it should be equal to 1. Yeah? It means that kd should equal 0 modulo p minus 1. Yeah? Yeah, like this. I believe that d should be something like should be like p minus 1 divided by GCD of p minus 1 and k. Yeah, I think it looks like this. And now I need to calculate the number of And now I can iterate through all possible values of this greatest common divisor. Now, if I know the value of greatest common divisor, I need to find the number of k's which have this value of greater common divisor with p minus 1. And how to do it? Let me think. It's too complicated. I'll start to write and then I'll continue to think. To the left. Let's find all the divisors of this long x equal to this. So now I find all the divisors of p. P minus 1. Yeah. Now let's try through all possible divisors. I still no idea what to do next, but I will continue. So I have this denominator. So that's this denominator, and I know this d. So I need to. So this will be p minus 1. I have d here, so let's remember. Oh, thanks. I have no idea what does it mean. All this cheat and all these things. I'm very bit streamer, sorry. So now I know this D, and now I need to add, yeah, here we go. I need to add D multiplied by something, some number. Not enormous, it's pretty small numbers. Okay, now the only thing is left is to find the number of such elements. So for each value of GCD, we need to find the number of k's such that GCD of p minus 1 and k is this value. How to do it? So I have this divisor. So I want all integers which divide by this and do not divide by any bigger divisors. Yeah. So I want to have all multiples of D, which are not multiples of any other divisor of p minus 1. What I can do, I can subtract all elements. So if for each divisor I take all bigger divisors. So what's the number of divisors? Is it big? What may be the number of different divisors of this P? Can it be too big? Can I do it in n square? So what I want to do, I want to take, so you have divisor D, yeah? So you want to have all numbers which are multiples of D. So I have all these two numbers. And now I want to remove all numbers which have bigger divisors. So I want to remove like all numbers which have bigger GCD. So I want to take, for example, this 2D and remove all numbers which have GCD equal to 2D. What is the easiest way to do it? How to find all big divisors? So I need for given divisors, find all bigger divisors. What is the easiest way to do it? I don't want to factorize it. Yes, you may factorize this number p minus 1 and split this d into primes, and now each next will be just this d plus something. Around cubic root, so it's 10 times 4. So it should be fine to work in n square time. Let's try. If it will not pass the time limit, we will try to fix it. Let's try. I'll just sort this. I'll sort this array, and then for each number I will calculate what I want to calculate. This. So I will go for I'll take each number. So what will be the value? So first number I will be just pi p minus 1 divided by div I. And now I remove all elements to the right. I need to think about 0 actually. What's wrong about 0? Is 0 some special element or not? No, let's change. What's going on when I have 0? When I have 0, I have something strange here when I have k equal to 0. K is not 0. K is... What is k? So k is here. Yeah, but if k is equal to 0 is some special case again. I hate special cases. Okay, let's finish this. Now equal minus and let's remove 0 from here. Let's bring g power p minus 1. So I have numbers from 1 to p minus 1. From 1 to p minus 1. Yes, that's better. It's easier to think. So I have numbers from 1 to p minus 1, and I want to have all numbers which are divisible by this divisor. So the number of these integers is p minus 1 divided by this. And now I need to remove all integers which have a better divisor. Well, try for all j's from plus 1, j less than n, j plus plus. So if this divisor is better than me, so it's divided by div I equal to 0. Then I need to remove these values from my, so now I should be minus equal num j. Yeah, I think that's what we're looking for. So x equal to 0 is a special case. That's right. Let's add it here. Should be fine. It's a very strange program. I don't believe it will work. But I will submit it anyway. Yep. It was expected actually. Oh, but it's working on examples. That's actually strange. Do I have some overflow problem? Oh yes, I might have a overflow problem here, right? If it is the only bug, that's actually wow, wow. And it's actually pretty fast. So what is the maximal number of divisors? That's what's interesting. So for the number up to but it's not like any number. It's number prime minus 1, so there's no many cases. So it's pretty hard to construct number in form of prime number minus 1, which have too many divisors. It's actually interesting. So if you have number p minus 1, the number of divisors is very small. You learn something every day. Today we learned this. Okay. Cool. Thank you for your suggestion, actually. Yeah. A suggestion about taking the generator and then continue from this. Was the key idea for this solution. Cool. Okay, last one, and we have 20 minutes until I need to go away. Given a positive and interesting again sequence of k integer. Okay. I need to remember this. All this time I didn't show you. So you didn't see this perfect result. So this solution was pretty fast actually. So it's 160. So the number of these divisors is about like 1,000 or something like this. So this part is actually very fast. Again, what I want to do, what's going on in this problem, in this part? I want to calculate the number of elements which have GCD equal to this I, this div I. How to calculate this number? I take all elements which are divisible by this div I. So this is the total number of all elements which have this divider. And now, so for all these elements, this divisor, this GCD is either this div I or it is more than div I. So now I take all these elements and then remove all elements which have bigger GCD. So I iterate over all bigger GCDs and just remove these numbers from it. So for all elements to the right, for all these J's, this num is actually the exact number of this GCD just by induction. So we go from right to left. For each number is the number of elements which have GCD equal to this. So for my numbers, for these numbers, GCD is either this or something bigger than this. So I take all elements and then remove everything bigger than this. So just remove, and that's all. So just by induction, I go from right to left. Every value is calculated correctly. So I take the next value. I know all values to the right are calculated correctly. So I subtract these values from the right, and this will give me y result, and so on. Yeah, if you think about exclusion principle, that's like you already implemented exclusion principle for all right values. So when you use it to your value, you kind of you use these values which are already some of these exclusion principles for these elements. So you can not use the whole part, but you just use these parts already pre-calculated in the right part of your array, something like that. Whew. Cool. We have 20 minutes for the last problem. Given a positive integers n, k, and sequence of k integers. Okay, shall we play again with stones? Initially with some heaps of stones, if you there's more stones. Play take turns to do an operation to cache again false. Choose a heap with one or more stones remaining. Remove any number of stones between 1 and x from this heap. So it's usual name. Okay. The player who first gets unable to do operation loses. Looks like a normal NIM game, right? Counting. It looks. Now it's complicated. Now, consider the initial arrangement of stones satisfying the following. I have no more than heaps. The number of stones is one of the following. What? What is A? So array A is given, K is given. I don't get it. So I have K values A. Okay. So I have M heaps. And the value in each heap is one of these given values. Okay, makes sense. I'm always scared when I have power 16. I think, what's going on? If this 10 power 16 is too much, but 2 power 16 is pretty small. 2 power 16 is something like 30,000. So I have like 40,000 of integers. Each integer is 16-bit integer. And I have, what is n? Again, what is n? N is the maximal number of heaps. So I have big number of heaps, but okay. Okay, it doesn't look interesting. So what's the interesting part? So what we need to do? So what we need to do is to take this array of A's and find the number of ways to take some integers from this array, such that the XOR of these integers is 0. Problem is I have too many. So if to present, I can't multiply it by this 30,000, or can I? Can I multiply this 2.8 by this? And multiplied by k is enough, or much? 2 seconds. 5 here I have like something 4, but it's too much. So I can't do it. N multiplied by k is too much. So each time I take new integers like this. Interesting. I don't know even how to solve it in L multiplied by k time. I think I know how to do it using fast Fourier transformation. Do they really want me to do fast Fourier transformation today? It wasn't my plan for today. Interesting. So again, what's going on? We have some elements, yeah? And we want each of these elements be from the set A. And we want the XOR of these elements equal to 0. Again, for example, if I want not less than n elements, but if I want exactly n elements, if I want to have exactly n elements, and I want the sum of this, XOR of this element will be equal to 0, what I can do, I can split this element into 2, and n over 2 elements here, and n over 2 elements here. And then if the XOR equal to x, I have some element A element here, then the result of x will be sum for all left A, let's say I, and this will be x XOR I multiplied by right x XOR I, something like that. This can be calculated in n log n, but I don't want to do it. Is there an easier way to solve this? I don't see if there's an easy way to solve this. No, another problem is that we don't want to have n, but we have some m which is not more than n. But I think it's not a problem. Yeah, I think it's not a problem. It's not a problem since we have okay. Let's have n elements, but we allow some last elements be zeros. Yeah, so these elements will be zeros, and these elements will belong to us. So we can do it in the same way. We have these elements n over 2 here. So it's either these elements and these are zeros, or there are these elements. So we have all these elements plus something from these plus zeros. Okay, let's do it. Let's do it. Can I do it in 8 minutes? No, no, I can't. I will copy XOR convolution from somewhere. Where can I copy XOR convolution from? I will not write XOR convolution. I don't know how to write XOR convolution. I'm not a real mathematician. Yeah. Can you give me the code? Just give me the code. Stop explaining. Just stop it. I don't want to learn it. I just want to copy the code. What is add? What is get? Что это такое? Дайте мне просто код. Yes, copy code from tourist. Yes, it's a good idea. What's wrong? What's wrong with you? Hate when it happens. What's wrong with you? So just multiplies. Nice. Cool. Okay, so now we just need to find the... Yeah. Who wins? So who first is controls kills this bounded to the gesture first instead? Who goes first? Takashi goes first. We need Takashi win, so it's not zero. So we calculate values of not zeros. Not zero. Count everything else. He calculated without model. There is no model here. Okay, we'll take model later. Nah. I want to add model everywhere. Measure calculate values after direct. What? Let me think. Paste model classes, it's a good idea, yeah. It's too long. Let's keep it something that way. Without batteries, I'm not sure how. What? Yeah, let's hold this way. This way I kind of understand what's going on. Time is left. I kind of understand what you're talking about, but again, I'm not really a mathematician. So when you call the first element this element, you kind of build these values of this polynomial. And what we need is to calculate the product of these polynomials. So the value in this point will be product of this. Yeah. Interesting. how calculate this function, like something those function something. Yes, I understand the geometric progression some. Yes, I think. Yes, and I can divide. If it's not 0, I can divide. Yes, and I can divide by this. Yeah, it should be fun. You know, I'm thinking about the whole algorithm. So and just to break this. Usually I don't want to break someone else's code. Okay, let's go. So what's the plan? First window, this is so we'll build this array. So we'll build this array for each. Now we will need this. So for int log size k. Not size k. I want size 16. No, I have this array A, so it's array S. I have this S. Great. B. B A I 1. Yeah. And now I want to call the Marcus formation for this B. Yes. And now, yes, I want to calculate these things. So now for each element I want to put geometric progression here. So I want to put pi equal to so I want to have from 0, from 1 I plus b I 2 plus b I power 3 plus and so on plus and so on plus b I power n power. So that's the plan. So this will be so this multiplied by this. Алло? Да? Да? Все так? Все Хорошо, спасибо. Sorry, I need to make a short break. I will come back in like an hour and finish this, okay? So that's why it's so. Okay, it took longer than expected, but I will come back and finish this, okay? Stay tuned. Yes, I'm back again. Let's finish this code. Oh. Okay. I'll try to do it as fast as possible. So we need to calculate this sum. This sum is actually bi power n minus n plus 1 minus bi divided by n minus 1, right? Yeah. So we need like power bi n plus 1 minus bi multiplied by inverse of n minus 1. Let's do the end. The end will be we need to do this. Yeah. So we'll need to do all this stuff, and then make another transformation of b. Then b inverse of n. Then let's multiply. And this will be the result. Yes, then n. Like this. Yep. So we finally need to implement this inverse and this power. Let's go. So we can remove this. Okay, so this is just a code stealed from the tourist archive. Okay. Let's go. So we need power. It's just like usual. Right? And finally inverse. Looks fine. Here some magic happens. So here some magic happens. So what we do here, we basically do the following. We calculate the Hadamard transformation for this array B. So this array B contains a number of ways to get this value of the XOR function. So for one column, for one tile, how is it called here? Heaps. Okay. For one heap of stones, the number of ways to get XOR equal to this AI is 1. Is just take this, yes, this number as the number of stones in this heap. So these numbers, number of ways to get this XOR for this function. And now we just need to apply it up to m times. So we apply Hadamard transformation. We'll get the values of this polynomial And then for each value of the polynomial, we'll modify it. So instead of taking one column, we'll take up to n columns. So the number of ways will be this. Now this is sum of geometrical progression. The sum of this geometrical progression is this. So we'll simply implement this. This is power of this n plus 1 minus bi. Multiply by inverse value of this. Let's say bi. Then let's see if like this. So we apply this function, and now we apply the reverse Hadamard transformation. So apply Hadamard transformation and divide everything by n. So here we divide everything by n. That's all. Now in the end we have this. So here we just calculate the number of ways to get all XORs except 0. So we iterate all values from 1 to n, so yeah, all values except 0, and take the sum of all these values. It's b. It's b. B here, b here, and b here. Yeah. So that's all. Some magic, okay? On time. That's strange. Like always runtime. Always runtime. Oh no, sometimes we have wrong answer. Let's see, nk and b the map up to n a plus modify apply. How can I get runtime here? Invert multiply and mode looks fine. How can I get runtime exception here? So the length of this array must be power of 2. It is power of 2 because it is m. M is power of 2. What can possibly go wrong? How can I get runtime exception? What's here? Yep. Yep. Okay, now it's wrong answer. Like always. Okay, let's try to debug. 31. That's obviously too much. Can you just spawn? What? Don't get it. I'm writing the wrong program. Okay. Oh. So something really bad happening here. Something really bad is happening here. Let's make one. Oh, no. I want to see it too. I want to pick only one heap. And the size should be 1 or 2. So I will win in both cases. Let's think like this. Let's look on this array. So what's going on when I apply this magic? I have all zeros. What? Let's move back. Let's move back. What? So n is 1, so we have 2 power 2 minus 2, so it's 4 minus 2. Am I crazy? What's going on here? Looks fine. What's wrong? How can it be 0? What? What? n is 1, so n minus 1 is 0. So I want to calculate inverse of 0. And because I'm doing something crazy, so it's not, it should be I minus 1. Yeah. And if bi is equal to 1, then bi should be n, right? It's like sum of n's. Else it should be this. Eight. How can it be 8? What? By m. Too many small bugs. Not even close. Yeah, it's because I use. Okay, now it's close. Whew. Now I'm not sure why this problem is in basic contest. So what people do think about it. So even this table is not supposed to have that many problems. Okay, so Gennady spent like half an hour to solve these problems. Good for him. So we spent slightly more than 2 hours. Okay. Look at the tutorial. Maybe we missed something. Maybe we missed something. Yes, this problem is pretty awesome. Yeah, it's kind of the same thing we implemented. Yes, here we have very strange binary search implementation. Yeah, so this solution is kind of the same. Yeah, this was the same idea. So we have primitive root. Yes, that's exactly the same formula we had. The English P times so optimize before this is FG FG can be replaced as D squared time. Yeah, that's what we did. Yeah. Highly composite number less than interesting. So the maximum number of divisors is actually about 7,000. So D squared is perfectly fine. Cool. And what about the last one? Yes, we use my transformation. Yep. It's exactly what we did. So you have this code. That's geometrical progression. Okay. Yes, I have a Martin transformation, then apply a function, then apply another Martin transformation, and then complete the. Okay. It's very close to our solution. I still don't understand why this problem is in basic contest. Should I have one more? Before we go to sleep. Let's solve one more contest. Because there is this give persist uppercase split if lowercase split. Okay. It's one letter. Okay, move to the next problem. Some kind of fruits and prices. Here we'll choose K kind of fruits and buy one of each. Find the minimum possible total price. Okay. Now we what's the game? The game is to solve all the problems without local testing. Looks fine. It's C++, yes, it's C++, but it's not idea. The idea is to solve all the problems of the contest without local testing from the first try. Okay, mini dog suddenly appeared under the roof of the house, which we can say to keep a bit numbered from 1 to this, okay. But he gave them names. The dogs numbered 1 to 6, precisely in Z. Okay, numbered from 2. So we use all 1-letter strings, then we use 2-letter strings, then we use all 3-letter strings, and so on, and so on. Okay, what's the website? Yeah, nah. How to take? How to show the I forgot. I forgot how to show the how it's called. Always show on screen. Oh, it's fine. Control Command F. Okay. What is the name of the dog number n? And we need to get this name. Okay. So we have the name, or we have the index of the dog, and we need to find the name of this dog. Okay, let's go. Let's find first. Let's find the length of this name. So we'll trade for like this. So we'll calculate the number of number of dogs of this length. So the number of dogs of this length will be the previous number multiplied by 26. So if n is more than s, then I just skip all these dogs. So I just add n minus equal s and move to the next len. It is a donation system. Why? It's too difficult. If not, then we know the length. So now we need to find the string itself. So how to find? Basically, what we need is to make n minus minus, and now we just need to put this integer n into 24-digit system. Yeah. So we do it like this. So we take the next digit. Digit will be n modulo 26. Add this digit as a letter. To our string, and then remove it. So that's basically how you move your number to some counting system. So we have 26 digits, so that's how we do it. Yeah, that's fine. And now, since we put digits from right to left, we'll just reverse this string. You can just add letters to the left, but that's fine. So digit 0 is A, digit 1 is B, and so on. So for example, here I have 2, so here I have -1. So I need to find the number 1 in this instance, so it will be 2. Here I have 27, so first I skip first 26. So I skip first 26, move to len 2, and then n equal to 0 here. So I get it. Looks fine. Okay. It's 3 of 6. You have sequence composed of n positive integers. You will not succeed do some operations. In the operation, you replace every element with values bi with ci. Okay. For each I, find si the sum of all elements in A after the if operation. Why not? So what we need to do is basically calculate for each value number of elements equal to this value. Like this. So what we'll do, I will get the sum and then modify this sum every time I apply the operation. So first let's calculate the initial sum. It's long. So let's calculate the initial sum. And now let's calculate for each value number of elements equal to this value. So I will use these counters. So now this array contains the counters for each element. So for each value I know number of elements equal to this value. Now I know these values B and C. I want to change all elements B with value c. So how my sum will change? My sum will change the following way. I will remove all elements and here I have integer overflow. So I will remove all elements equal to b and then add the same elements equal to c. So this is how my sum will change. I remove x elements from the sum. So S is the sum of all elements. I remove these sums from this sum and add these sums to this sum. So this is how my sum will change. And now I modify my counter. So I simply like this. Okay, go to 0. And plus equal x. Okay, let's do it just for symmetry. So just for the symmetry. So I remove these elements from here and add them to here. That's all. After any operation, so apply operation and then output the sum of all elements. Alright. Yep. Just some other flows. Here I don't have any overflows. Here I don't have S. I don't have overflows here. That looks fine. Okay, 4 out of 6. 2 left. Now n cats numbered one is this number n is even. Okay, n is even. Each cat wears a red scarf. Okay. On which his favorite non-negative integer is written. Okay. Recently valid plus and hot XOR. Okay. They want to use this operation quickly, so each of them calculated the XOR of the integers written on their scarf except his scarf. We know that the XOR calculated by Snoopcat is I. What? Aha, so we know the value calculated. Using this information, restore the integer written on the scarf on each cat. So for each element, we know the XOR of all elements except this element. I see. So what these elements are? So here 20 is XOR of these 3 elements. 11 is XOR of all elements except this 5, and so on. So how XOR is calculated? XOR is a very simple function. XOR of self-inversible. So XOR of all elements except 1 is XOR of all elements XOR this element. So if we know XOR of all elements, then we can calculate each element just by using this XOR. So we get XOR of all elements and XOR it with this value, and it will give us the result value. But we need to know the XOR of all elements. How to know XOR of all elements? Very simple way. We'll just XOR all the values here, and it will give us the XOR of all elements. So basically, it's a self-inversible function when n is even. So again, we have this n. Yes, I forgot. 9, yeah, that's fine. There exists a combination of integers. Yeah, there also exists. So first we calculate the sum of all elements. So this will be the sum of all elements. Again, since we have even number of elements, if we calculate XOR of all these values, it will give us the XOR of all elements, because every element will appear odd number of times in this sequence. Yeah? So again, this element is XOR of these elements, this element is XOR of these elements. If we calculate XOR of all these elements, then first element will appear 3 times. Yes, for these 3 elements. So this element will appear 3 times in this final XOR. 3 is odd number, so it will appear in the final XOR sum. And so on. So this S is actually XOR of this sequence. So we calculated this XOR of this sequence, yeah? But XOR of this sequence will be the same. And now we simply find the result. That's all. Oh. Okay, and the final one. Okay, this contest is much easier than the previous one. Final problem. How many strings can I obtain by applying the following operation string exactly 8 times? Choose one lowercase n set and insert it somewhere. Ooh. 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 That's interesting. What do you mean insert it somewhere? Okay, no, just in any place. So we will insert 5 letters into this string at some positions. We can insert before the start, we can insert after the end. Like here. We need to find a number of different strings. These constraints are actually scary. These constraints are actually scary. I also posted the link. Let me do it again. So basically what we need to calculate, we have our string and plus we inserted some letters. So we want to calculate number of different strings which contain our string as a subsequence. Yep. Some paper. So what we have here, for example, here we have string oof. So we want to calculate, for example, let's say moonwolf. So this string is good because we can get it by applying. So if you look on this string, so we have this letter O here, and letter F here. So our string appears in this string as a substring, as a subsequence. And we want to calculate the number of different strings like this. Interesting. So let's do the following. So how to solve this problem slowly? So how to solve the problem slowly? So we just go from left to right. Let's build this string S. So string S, what is called? So this is string S. Yeah, so let's call this string T. So now let's try to build the string T. We'll go from left to right, yeah, and put the character. So how to check if string T contains string S as a substring? We can do it greedily. So if you have some string, let's say T equal to let's see some A, O, O, P, O, A, F, O, O, F, M, and so on. So, how to find if the string contains here a substring? We can do it greasily. Just go from left to right, and the first time you see the character, you pick this character. So you can go from left to right, pick the leftmost O, leftmost A, then skip this. Now looking for F, so we find this F, and so on. And now it's finished. So for each string, we can find like the leftmost appearance of this string. Okay? So for string T, we find the leftmost appearance of string S. Now let's try to build this string T and this appearance of string S. So we go from left to right. So each time we build some prefix of this T. So let's say let's say O, P, O, and we're standing here. So if we're standing here, we need to remember the number of characters we already know. So we know these two characters, and we're standing here. So standing here, we're looking for character F. So what's going on from this point? From this point, we can add character F and pick this character. Or we can pick any other character. So we can pick any character, not F. We can pick any other character and stay in the same position. So from every point, we have one character which moves us one position to the right, and 25 characters which gives us the same position. So how dynamic programming? So let's say we have dp of I and j. We have I characters here, and we have j characters already picked. So we have no. Let's make recursive function easier. Let's have dij. Let's move it backwards. So the last character is good. It's one way to pick the good character. So it be di minus 1 j minus 1 plus 25 wrong characters. 25 di minus y j. Now what we need to basically to calculate this dynamic programming. So if these numbers are, if both these numbers was small, so if this length is this, so we can just implement this dynamic programming. The complexity of this dynamic programming is actually n squared, right? So both this I and j are squared. The interesting thing is that this dynamic programming actually doesn't care about this string s. So we actually don't care about the string s. Interesting thing, right? So this answer is actually independent from this string s. We only need the length of this string. Only the length of the string matters. So we have this and we have this and we need to calculate this. Now we just need to find the fast way to calculate this sum. That's interesting. So there's another way to think about this. So it looks like a usual how it called combinations from. So look. So if you remove this 25, that's just simple number of combinations from n elements to pick k elements from given n elements, right? So it's like usual binomial coefficients, right? This 25 is actually so what's happening actually, you can think about this problem like this. So you pick some positions and put good characters in the positions, and you pick other positions and put some bad characters in other positions. And there is always one good character for each position and 25 bad characters for each position. So you just pick these positions, then put these characters of string s into these positions, and put some bad characters into all other positions. And there is always one way to put these positions and 25 ways to put these positions. That's all. That's how we will calculate this. So the answer is actually number of combinations from n plus k. Okay, so it's number of ways to pick these characters. Multiply by 25 power k. So I claim this is the answer. Oh, now let's just implement this. So this number is actually 25 power 5. Modulo this. Maybe. So all numbers are pretty big, so it doesn't spoil the formula. Okay, let's go. So we have this k, we have string s, and n is just the size of this. Yep, and now we just need to calculate this. Yeah, so we'll do this. So once again we need to implement all this modular arithmetics. So what's the plan? So result will be number of combinations from n plus k by k. Let's use this one. So how to calculate this? We'll calculate this by taking factorial of n multiplied by factorial of reverse factorial of n multiply by inverse of factorial of k. So this is our binomial coefficient, and then we'll multiply it by 25 power k. It's small, so we can just avoid this. But we still need inverse. I still need to implement this. So let's go. So again, we did it like a few minutes ago. And I cannot do it from the first try. Okay, now we'll calculate factorials. I actually don't need this array, but and now we implement inverse. Now don't remember to take model every time. So I'll do it like this. I have this, then yeah, I multiply by this, multiply by this, and multiply by this. Now every time I'll take modulo. Again, usually you have the special like library for these modular calculations, but I don't use it. Is it fine? So again, I have this array of factorials. Factorial of 0 is 1. Now for each n from 1 to n plus k, I have factorial of I equal factorial of I minus 1 multiplied by I modulo mod. Okay, now result is factorial of n plus k divided by factorial n divided by factorial k. So it's number of combinations from n plus k to k, or to n, it doesn't matter. So it's number of ways to choose these positions. Now for all k positions, I have 25 ways to choose. So I multiply it by power of 25k. Now let's read this again. So it's normal binary power of but let's try to multiply by a square, but divide. Okay, that's fine. Looks fine. Did I miss something? I'm a little bit scared because we solved all the previous problems. So we have 5 correct submissions, and that's the final problem of this contest. So if we solve this problem, we have the whole contest solved from the first try. So it's kind of scary. So we have this K, S, S, N. Okay, let's do it. Let's do it. You can have a string of, for example, I can. Oh, it's a good point. It's a good point. In the end, we have some letters in there. Good point. Let's move back to the paper. So we have some good positions, some bad positions. Yes. So we have some positions are good. So when you go from left to right, these positions contain some bad characters and these positions contain some good characters. So for these positions, you have one possible way to choose character. For these positions, you have 25 positions. And for these positions, you have 26 possible ways. So we need to find a way to count these things separately. Nice. So we finally need to do something. So let's iterate over this position. So let's find it with this position. Oh, or we can iterate a number of characters in the end. Something. So let's iterate over this position. So we know this position of the last character. So we calculate number of ways to choose these positions here. Here we know everything, and we know for this we have 26. Yeah, I think that's better. Okay, let's fix this. Let's put this in front. So and just move it to the front. I'll calculate inverse value here, but no, that's fine. Yeah. Fact K Remove this. So what we'll do, we'll iterate over this position of the last character of string s. So the position of this character will be from so we have n characters, yeah. So its position is at least n minus 1 and less than n plus k. So I is the position of the last character of the string. And now we will calculate number of ways to get this situation. Get this situation, we need to put this n minus 1 characters in the first positions. So it's number of ways to choose from I positions some n minus 1 positions. So it's number of ways to choose these positions. Now we will multiply this result by these 25s. So we have 25 in power, so number of these wrong positions is I minus n minus 1. So it's number of these bad positions. And now we have these positions. So number of these positions is n plus k minus 1 minus I, right? N plus k minus 1 minus I. Yes. So it's the number of these wrong positions. Yes, now just edit results. Is it better now? Now it should work, right? Okay, I'm a little bit scared, but it should work. Again, we pick some n minus 1 positions. So we pick, so these positions, so we pick these n minus 1 positions from first I position. So this index is I, so we have I positions to the left from that position. So we pick n minus 1 from I. Let me just double check. Now we have I minus n minus I wrong position. So for each wrong positions we have 25 possible letters. And now we have these positions. For these positions we have n plus k minus 1 minus 1 minus I. And so that's easy to check. The sum of these two values should be n plus k minus n. So sum of these two values should be k. So it's I minus n plus 1. And here we have I minus n plus 1. So sum of these two values is k. So we have k wrong positions. We have these number of positions here and these number of positions here. Okay, the most sad thing will be to have some integer overflow at some point. Nah, looks fine. Should work. Should work. Fingers crossed. Okay. Okay, that was fun. Okay, in this optimistic note, we will finish this stream. Thank you for joining me. You didn't see. Yeah. But binary search. Yeah, I have the whole lesson about binary search on Codeforces. It's great. Whew. Cool. So see you next time. I don't know when. Maybe tomorrow. No, tomorrow is the Richter stream. I'm trying to not interact with Erichto stream because I'm trying to put it in different days from Erichto. So maybe on maybe on Wednesday. He streams on Tuesdays and Thursdays, right? So maybe on Wednesday. I don't know. The problem is I covers most of the topics in my ITMO course of lectures. So I just don't want to repeat the topics which I already covered in these lectures. It's actually different. I repeat this also. I have the, for example, segment tree in the Codeforces course, and I have the segment tree in my lectures, and they're slightly different. Maybe it's fine to have another lecture which kind of repeats the same topic. Yeah, I don't know. Where can you access your ITMO course material and videos? On YouTube. No, everything I ever done is on my YouTube channel. Everything is here, so here are all the lectures. 12,000. Okay. Actually, most people try the first lecture and decide it's not for them. So I have 12,000 views here and 3,000 views here. So most people understand after the first lecture that it's just not for them. But we will, in the next semester again, we'll start next semester in September, and we will talk about graphs. We'll discuss everything about graphs. DFS, BFFs, shortest paths, and graph games, and something, I don't know, what else, spanning trees, stuff like that. So we'll talk about all this in the next semester. Which is next episode? I don't know, maybe we'll do it on Wednesday, I think. We have a lot of stuff to do. We have many problems. This is scary. This is scary. Okay. Have a lot of stuff to do. Okay, but this was interesting. The node very sound because cells and deeper. What do you mean? So. I mean, when you already read it off? Okay. Yeah. I think it's kind of the same. It happens sometimes, even for me. So sometimes I watch some lectures. For example, in mathematical logic, that's one of the most strange topic for me. So usually I watch the lectures. I watch the first lecture and it's everything clear. I watch the second lecture, it's somewhat clear. And in the third lecture, I just don't understand anything what's going on. So. Matching. We will talk about matchings in the fourth semester. In the fourth semester, we will talk about matchings, flows, everything about matchings and flows. Yeah. So the first semester will be about graph algorithms without flows and matchings, and about string algorithms. We'll talk about everything strings, like Knut-Morris-Pratt, about hashes, Z algorithm, Aho-Karasik, Ukanin, stuff like this, everything. Okay, so see you next time, maybe on Wednesday, maybe not. I'm not sure. We have this top coil on Wednesday, right? But it's in middle of the day, I think. So maybe after the top coil original, we'll have the next stream. We'll see. Okay. So see you. Thank you for coming.